The next presentation is going to be a comment on natural mortality by Kai, and I see him, he's all ready to go. So Kai, do you want to put up your presentation share your screen?
Okay, yeah, let me see if can you hear me?
Yes, we can hear you nice and clearly.
Okay.
Yeah.
So do you want to continue? Yes. Okay. And now you can see a presentation, hopefully. And it should. Okay. So you can see my.
Yes, and we can see it in full screen too. It's good.
Perfect. Okay, well, thanks, Mark, for the introduction, and thanks for inviting me. I'm sorry I can't be with you in person. So I want to offer a little comment on natural mortality in tunas. And I want to start with a disclaimer here. So I've been very intrigued by tuna natural mortality patterns ever since John Hampton's Size Matters paper, partly because I, of course, agree that size matters, but I focused mostly on the declining limb on the left. And so I always use this as an example of, well, and then there are some stocks where you might expect an increase in older age or at larger sizes because of senescence or cost of reproduction, and so this is close to my heart. But other than that, my extent of interacting with tuna is sort of depicted accurately in that little picture on the lower right. So taking stock of where we are, I want to congratulate Simon and his co-authors on a really excellent keynote. And I think it's a really good synthesis of our understanding of natural mortality concepts, models, estimation, and good practices for tunas. But it seems to me, sort of looking at all of that, and I would have made a lot of the same arguments, that aren't we really all at sea about the origin, modeling, and estimation of these complex M patterns that we seem to be seeing in tunas? And so I want to talk about that a little bit, and then I want to give you a new perspective that actually occurred to me like 2 days ago while I was putting my presentations together. And it really occurred because you guys made me give the comment on both mortality and growth. And so I looked at both, and that led to some interesting insights. So this is from Simon's presentation. Obviously, we're looking at very different natural mortality patterns being assumed in different stock assessments. This is all for yellowfin. And Simon was sort of alluding to more or less, I think, wanting to have a more unified pattern. And I'm looking at this, so I'm looking at the Atlantic, for example, and I'm looking at the Western Pacific. And so there's one pattern that has that bump and one pattern that doesn't. And I want to, for the moment, think maybe they are actually different. And I'll come to why I think they might well be actually different in a moment. So dealing with all those different patterns, this is the, again, from Simon's talk and paper. It's sort of an outline of the concept of natural mortality that we apply to tunas. And so there are all the reasons why mortality might decline in smaller, younger fish, particularly to do with predation. And then there are the things that might lead to it increasing in older age. And the main things here are essentially a cost of spawning, a cost of maturation, a survival cost of maturation, and then there is senescence. And when you think about tunas, there might be good reasons why you would observe some level of senescence in tunas, because one of the ideas behind senescence is there are processes that are linked to metabolism, like oxidative damage, that lead to senescence. And basically, if you have a really high metabolism, you should experience more of that. So it's a sort of live fast, die young hypothesis. And then in terms of cost of reproduction, survival cost of maturation and reproduction, there's actually not a hell of a lot of evidence for that being a big thing in teleosts, other than obviously the Semmelparo species. And also, my question has always been, so why would it be so different? Why would we see a lot of that in some of the Pacific yellowfins, but not in the Atlantic? And so why should this be such a different factor? So from that the concept, we get to what Simon just outlined. There's sort of basically two big picture different models. There's the declining curve, the Lorentzian curve, and then there is that two-stage model, which I'm glad is a slight simplification of Mark Maunder's hideously complex 5 or 6 parameter mortality model. But it basically has that initial decline, and then it goes back up to a higher level of mortality. And so those are the models that we had on the table. And of course, then there's all the tagging natural mortality estimates. There's Hampton's and Peatman's et al.'s recent re-estimation. And those show somewhat different patterns. So both of these have clear sort of bumps, if you like. They also have overall higher levels of mortality, and Simon went into some detail as to why we might find that. But let me, at this stage, just re-emphasize that actually we have some quite different ideas, models, and quite different mortality patterns on the table here. And I don't think those patterns are quite on the same page yet. So the two-stage model, and this is just grabbed from the paper. Obviously, it's basically a way of taking all the bits of this mortality puzzle and saying, well, I want to use this bit and this bit and this bit, and I think that makes sense. And so, and I just want to provide a few thoughts on that. One is that, the big thought here is about survival cost of maturation and reproduction. And my question is that really the mechanism that we should be looking at? Then there's an initial decline with a slope of or a scaling of -1.5. Of course, I believe that should be a -1. There's use of Tmax-based or growth-based estimators of natural mortality in the adult population. And I have some comment on that towards the very end. And then there's also, and I thought this was a little funny, so there's a juvenile M here, which uses my old 1996 paper, which actually shows us that lambda should be about -1. So there's sort of actually two different bits in here that don't quite fit together. But, it's what you do when you try and come up with something that represents your thoughts on the subject, right? So what I want to do is I want to take you to kind of the generalization of the Lorentzian curve, which I call the generalized length inverse mortality paradigm. And of course, the core of that is that on average, the lifetime mortality scales with about the inverse of length, and it's modified in juveniles by density dependence, and it might be modified in old fish by senescence. The important thing is that also so we have basically a constant scaling, but then that curve moves up and down, and actually the intercept of that curve is very much related to growth. And this is something that we found in the empirical paper on this we published last year. And so basically you can see on the right-hand side, you can see different mortality curves that are they all have the same scaling of, they're all length inverse. But the intercepts actually are very closely related to growth or to the maximum growth rate. So if you calculate the maximum growth rate as k times L infinity, that provides you with a predictive relationship for where that intercept should be. And of course, that's also, the basis of, a growth-based M estimator, so to speak, that you can apply to the intercept. And we did that in that paper, and it's actually quite, it's certainly not really different from the Then model. So sort of the same, gives us the same general model. Now, the important part for today is, okay, and of course you have the tunas being very high on the growth rate, and they also would be very high on that mortality trajectory, right? Now, what gave me pause and some new thoughts is when I worked on the growth comment for tomorrow, I was looking at growth patterns, and as you can see here, some tunas actually have very distinct growth patterns that involve two stages of growth. And these are all from the Indian Ocean. And so basically I thought, well, if they're jumping from this growth trajectory onto that growth trajectory, what do they do in my world of natural mortality intercepts? Well, they would jump, right? They would jump to a higher level, well, in this case, a higher level, because the model here, this is the 1 battalion phi log K model, and this is from Paige Evenson's paper. And basically, this is a model that has one L infinity of 131 centimeters, and then it has two different Ks. So it has a very low K of 0.21 for the first stage, and then it has a much higher K of 1.54 for the second. And so if I take those parameters and plug them into the mortality intercept model, then this is what I get. So I have a lower mortality, lower mortality sort of curve here, and then it jumps up to a much higher mortality schedule as it jumps to the higher K. And of course, if you then take that and translate it back into M at H, you get something that looks like this. So you have Lorentz curve phase 1, and then it jumps up to Lorentz curve phase 2. And I think, if you have a change in growth schedule that is as dramatic as this, you're bound to see some of those changes in the mortality rates. So what this is sort of a very straightforward extension of Lorentz M to stocks that have marked two-phase growth schedules. It obviously simplifies to the standard Lorentz M when you have growth that broadly follows 1 battalion phi, and that is the case for the South Atlantic, for the Atlantic yellowfin. And so this is where I'm getting to the stage of saying, well, maybe the mortality pattern really is different for Atlantic yellowfin compared to, say, the Western Pacific or the Indian Ocean. And you have the reason why here. The neat thing is you don't have to buy this from me. It can be tested, because basically we should be able to see this if we compare growth curves and mortality schedules. Obviously, we should see a fairly strong effect of this sort, where we have a big phase transitions from very different growth patterns, and we should see very little or none of it in cases where that's not the case. So it's eminently testable. And obviously this whole thing can be improved by developing growth-based intercept predictors specifically for tuna. So what I was using here is the general model that has everything from little freshwater fish to, in fact, some tunas, but it's probably not a terribly good model specifically for tunas. So finally, I want to compare this a little bit. And so on the right here, I have, because the tagging data, it's all, the estimates are all length related. So I converted everything to length. And I want to show you what these different models look like. So there's the model that I just introduced. This is the two-phase Lorentz curve. And as I said, straight out of the box. So this is using just the overall best model for the intercepts. And it's using Page Evenson's growth model. Then we have the Indian Ocean model from Simon Hoyle, and you can see it has a somewhat different shape. It also has lower mortality levels, and I think a lot of that is to do with the scaling to the Tmax based estimate. But you can also see that, and unfortunately I didn't have a tagging study for the Indian Ocean that I could just put on here, so I'm pilfering from different stocks. This is the West Pacific tagging study, Peatman's estimates. And you can see that basically the pattern that the two-phase Renson model produces is not unlike the tagging data here. But remember, this is a different ocean. And so I wouldn't read too much into this, but it does give you an idea of the different pieces of information that we have on the table here for the yellowfin stocks under conditions where we might see a change in mortality and an increase with age. Okay, it's obviously possible to approximate the two-phase Lorentz-NEM with the two-stage curve that Simon Hoyle and others just proposed. And I'm not going to go into details, but obviously you could do that. I have one more comment, and that's really on the overall level of mortality and the Tmax-based versus growth-based M estimators. And the Tmax-based estimators obviously are generally seen as the gold standard, because certainly when you evaluate the predictive power on the data sets from which the models are derived, the Tmax-based estimators do better. So they're associated with greater predictive power. My concern is that in practice, I'm not sure that we're defining Tmax and using Tmax in ways that are really consistent across different studies, study designs and assessment approaches. And I think Simon commented on that a little bit in his paper in terms of tag-based ideas of estimating Tmax versus hard parts and so on. But I think it goes beyond that, because we need to think about, so what were the studies like that were put into that data set where the Tmax-based estimators were derived, and mostly those are relatively small studies published in academic journals. And now we're having these enormous data collection programs where we're collecting, tens of thousands of estimates. And I'm not sure that those are necessarily compatible. And actually, we often discount for some of that. So I've been in meetings where we said, yeah, well, the very oldest fish is 26, but that's maybe an outlier. So let's go with something, the next oldest, which is 18 or so. And even that may be older than what would have been put into the original estimator. And so I'm a little concerned that we're being overly confident in our use of the Tmax-based estimators. So it's not about the model as such, but the question is, does what we're putting into it really correspond to what the model is built for as a Tmax estimator. I think this is maybe the best way I could say it. Okay, last slide, quick conclusion. So I'm thinking M increasing with size and age may be linked to growth phase transitions, not maturation. Growth information can help identify the best structural mortality model. So it could be a Lorentzian curve if you have basically one battalion fee growth or something similar. It could be a two-phase model if you have a departure from that, and that could be expressed in the log K 1 battalion phi. It could be in the Richards. The reason I'm using the log K 1 battalion phi, of course, is that those parameters I can just take and put into my M1 predictor, whereas I'd have to find a way of translating the Richards into that same framework. Meta-analysis of Tuna growth and mortality schedules within this paradigm may yield a new set of M predictors, and I think we should really do that. And if someone is interested, be very interested in collaborating on that. And of course, the two-stage M that we discussed. And I'm getting the impression, Simon, you're kind of almost getting out of that, but I think, you know, it could be adapted to approximate the two-phase Lorentzian M, and it could also be, of course, modified in other ways that I briefly discussed. And that's all for today. Thank you.
Thanks, Kai. A very stimulating presentation. Gave me a couple of ideas, but I'll wait for other people to make comments before I mention what I think. Anyone have any questions or comments for Kai? No? Okay, then I'll say what I think. I've always been worried why you would scale back the natural mortality using a length relationship from the estimates of adult natural mortality for tunas, because yellowfin, big eye, and skipjack, you know, at the same sizes, you might expect them to have similar natural mortalities. So maybe the adults have different natural mortalities because of the lifespan, but why wouldn't the juveniles, particularly if they're all around the same fad and that, have the same natural mortality? And when you were presenting your presentation, it clicked right at the start that I thought this is what you were going to say, but you actually went somewhere else. And if it's predation that's causing the juvenile mortality, it's within a quarter of the model that we're modeling. How long does that fish stay within that size range so that predators can eat them? So the fish that grow faster when they're young, and faster I meaning in terms of how big they get in a quarter, should have less mortality, right? And I was wondering if that is somehow related to the shapes we see. And if you see a kink in the growth curve, then of course the mortality is going to change a bit because they're going to slow down, so they're going to be within a mortality range for a longer period of time or something like that. So I was wondering if that might explain why you would get different natural mortality for small fish between the three different species, and whether it's something worth looking into.
So I'm not sure I fully understood your argument, but I think, so what the key here is that basically if you're growing faster, that tends to be a mortality cost to that. So because basically you're it's and I was surprised to see it that clearly in our data when we did the intercept estimates, because of course that's a staple of ecology, the idea that faster growth comes with higher mortality, mostly because it requires you to expose yourself to more risk in order to get the resources to grow.
Yeah, mine was the other way around, where I was saying the faster you grow, the quicker you go through the predation window, so your natural mortality would be lower.
Well, it would eventually become lower, right? But while you're at the same size and growing faster, your mortality would be higher. And I think that's really the key of that that mortality intercept thing. And I was surprised that it came out so strongly, but because I mean it's something that ecologists always talk about, and I hadn't realized that it's right under our eyes and you know the mortality estimates that we do for fisheries. So.
Okay, anyone else got any comments for Kai or questions? Oh, we have one online. We have several online. Good. Paige, do you have a question?
Can everyone hear me?
A little quiet. Can you try and get closer to the mic or speak up?
Yeah. Is that better?
Yeah, much better. Thanks.
Good.
I guess I just felt I had to say something because the Evison curves, like, yes, I did estimate those curves. They were based almost entirely on tag recapture data from the IATTC tagging program. And I don't know if you've seen since then, but we've done a lot of aging of otoliths. So Jessica Farley's led that work. I've been part of it. And a new paper was submitted to the IATTC in 2021 with the otolith data, and it no longer shows that really extreme two-phase growth. And so we started thinking, what's the issue here? And I think Simon was actually at the meetings where we started to investigate this, and it's actually him that said, well, could we look at the length frequency data and see if we see anything in that? And it actually turned out that I don't know how much to go into this, but the tagging actually took place on only a couple of cohorts. And when we looked at the length frequency modal analysis of those, one of those cohorts was growing really quickly and the other one actually grew much slower, which in a tagging model, when you don't actually know a release age, the model has to try and estimate it. So even if fish are the same age, if you've got one group that's much larger for that same age, so the only way the model knows it just makes the bigger ones older. So it actually was, can actually be explained by different growth rates amongst cohorts. And I think the new otolith-based growth curve is actually a better one to use. It still shows a little bit of two-phase growth, but nothing nearly as extreme as that for both the yellowfin and for the big eye. So it doesn't change what you were investigating in terms of the links between M and growth. And if you do have two-phase growth, which we do see in southern bluefin tuna as well. So I'm not saying that it discounts that, but that actual extreme example, I actually don't, even though, yeah, my name is attributed to those growth curves, but I actually think they are no longer, I wouldn't trust them.
Yeah, well, thank you so much for the comment, and certainly also thank you for doing that paper in the first place, because even if it turns out to be nothing, it made me have an interesting thought. So, and I was actually thinking that it would be nice to try and collaborate. I found it extremely difficult to assemble and I was trying, scrambling on the weekend. I was thinking, okay, can I find a few, good growth curves and mortality data sets to test this, and of course it wasn't enough time, but I also realized that you have to really get into the thick of it to figure out which growth curves are better, and the same for the mortality information. And I think that is partly why we are a little bit at sea, I think. But so I think it would be really nice to try and do this on a basis where perhaps teams from different assessment teams and tuna fisheries could figure out what they regard as their best empirical patterns, and then we can put those together and actually attempt to do a little bit of a meta-analysis, because it's virtually impossible for me as someone who looks at tuna in tins, basically, to figure out what I should be using. Thank you.
Thanks. So we have another question by John Hampton.
Hi, everyone. Hi, Mark. Thanks. Just a quick comment, Mark, on your idea about comparable natural mortality rates at size across species. I would be very careful about including skipjack in that particular scheme. I mean, skipjack are just so different metabolically than yellowfin and big eye, which may well be a bit more similar. But skipjack are just so different. My old mate Bob Carney once said to me that skipjack are as different from yellowfin as yellowfin are different to sturgeon. Now, that might be a little bit of an exaggeration, but that was his point, that they are just very, very different critters. So I don't think there's much reason why we would expect them to have the same natural mortality rates at size.
Yeah, I kind of agree. But I think it also goes into the general sort of theory of length, mortality being a function of length, and then the maximum age for the adults and the predation thing. So it's always confused me a little bit, but something worth looking into. So now we can move on to questions on any topic on natural mortality for Kai and for Simon, or if Kai and Simon have any comments they want to make as well. Simon, yeah.
Yeah, I wanted to follow up on the point about the two-stage growth curve, and in the presentation today I didn't really talk about that because I was thinking about reasons for why we might expect it, and we don't really have any good evidence to suggest that it happens. So the information that we have does suggest that there's a declining curve, but the increasing natural mortality with age is more of a theory. And I think the evidence that we have from the tagging data, which some of the tagging data does seem to show it, and some of the, like the Pacific data does seem to show it, but the Indian Ocean data doesn't seem to show it at all. So, and I was looking at the Pacific data and thinking, well, that's quite likely there because the longline vessels are not reporting tag returns. So that seems like perhaps a sufficient explanation, and the Peatman et al. Paper tests for the evidence that there is an increasing natural mortality with age and doesn't find any. There's a suggestion of it, but there's no statistical significance in it. So for those reasons, I thought it was the best idea just to go with the Glim-Lorenzen curve and not worry about the other option.
Thanks, Simon.
Yeah, thank you. Oh, yeah, I'm kind of good with that too, but it's more interesting if more happens.
Yeah. So this change in natural mortality for females and whether it's true or not. Yeah, we're slowly getting a bit more information now that suggests maybe it wasn't the way to go, but still there's conflicting information in the tagging data and that, so we're not 100% sure. One thing I want to ask, so Kai, you've always said that there's very little evidence of increased natural mortality when individuals mature for fish. Tropical tunas are a little different because there's evidence that they spawn continuously as long as the water temperature is the right temperature. And in lots of places, the water temperature is the right temperature, so they're spawning every day. And I was wondering, is that life history quite different from most fish that would be in the databases you look at? And maybe in yellowfin in tropical tunas there might be some increase in mortality due to maturity, or maybe even growth as well, changes in growth when they mature. So
I think it's sort of confusing because if you look at the those growth curves, and I take Paige's comment that I shouldn't put too much trust in the magnitude of those changes, but it would tell you that those Indian Ocean yellowfin are actually growing extremely fast around the time they mature, right? And so, which seems to conflict with the idea that there should be a really strong impact of maturation as such on survival. Of course, you also have, you have information increasingly from captive tuna populations, and it seems that they're happily spawning all the time and not dying of it. Of course, you can't easily compare those because there may be sources of mortality associated with spawning that you don't find in captivity. But I still think that, if there should be a really high mortality cost associated with specifically that, you should be able to find some direct evidence for it. But I mean, that's, it's one of those things where we have some theoretical thoughts, but not a lot of evidence, I guess.
Okay, any other questions or comments on natural mortality? No. What about determining the natural mortality for the average adult based on maximum age? I mean, we've been through this several times, and there's things like Kai said, that the data sets that were used in the regression aren't really representative of applications that we want. So it's an empirical relationship. So it's basically saying we've got a whole lot of estimates of M, and if we have a stock that is represented by those, so it has the same kind of fishing mortality, it has the same kind of sampling and life history and stuff like that, then it will provide a good estimate. But if you get something that's different, like the sample size is a lot different, or the fishing mortality rate's a lot different, then the estimate of M is not going to be representative. So what do people think about the representativeness of that data set used for estimating those relationships and what we're looking at for tuna stocks? Yeah, Simon?
Yeah, I guess they are different in some ways, in that those stocks were chosen to have low exploitation rates, and the stocks we're looking at have generally much higher exploitation rates. In terms of sample sizes, in most cases, they're not all that different. Like in the Indian Ocean, it's I think a couple of hundred fish, and that's all. And in the Atlantic, certainly it's a lot more fish. It's, I think, a couple of thousand. I can't quite remember exactly, but still we're seeing 6 fish in that case, age 17 to 18. So I don't really think that that's a sample size issue. Chance effect that we've got a lot of fish and we're seeing just one really big fish, one really old fish, we're actually seeing a lot of old fish. So, and in the WCPO, I think it's there still aren't an awful lot of fish being aged. So in that sense, I don't think we are really dealing with massively different from the meta-analysis.
Okay, so what about the high exploitation rates and the theory that there's always going to be an old fish because they're hiding somewhere they're never going to get fished? I mean, is that a reasonable argument, or should we be worried because our exploitations are really high, so our maximum ages we're seeing are underestimates? Simon, you want to answer that one too?
As well. I think in the case of the Atlantic, there are more refuges potentially, because I think they were looking at recreational catch in areas that were to some extent around oil rigs where there's less fishing and potentially more refuges. Whereas in the WCPO and the Indian Ocean, a lot of the samples come from areas with higher fishing mortality. So we are seeing a difference there with younger fish, younger maximum ages in areas where there is higher fishing pressure So perhaps, yeah, maybe I'm making a circular argument there. Yeah, I'd better leave it there, I think.
I think it makes sense. But John Hampton, you have a question?
Yeah, just a comment, I guess. I think in terms of the WCPO, where we have good quantities of tagging data for skipjack, yellowfin and big eye, my first preference or first port of call would be to try to estimate the sort of asymptotic M internally in the assessment, assuming the Lorenzen age-specific pattern, and see how that works, see if it gives biologically plausible estimates. And of course, those can be compared with the AMAX sort of based estimates as well. But I mean, I think if you can estimate it with tagging data in the assessment, then it would probably be preferable to do that.
Okay, any other comments or questions? Yes, Simon?
I'd just like to ask, John, what would you do about the issue of the largest, oldest fish being less likely to be reported, given that they're being caught largely by longline fisheries, which really don't report tagged fish very much?
Okay, it's possibly true that the longline fisheries do not report at the same rate as others, but we do have, for what they're worth, the reporting rates in the assessment. So to the extent that the model estimates those more or less by comparison with fisheries that do have informative tag reporting rates, then some of that would be taken into account. I think in most of our assessments, the reporting rate for longline fisheries do come out pretty low. So to that extent, that would be incorporated. And there are at least some observations of these older fish in our tag data sets for each of the species.
Okay, thanks, John. One other aspect that we haven't talked about is temporal variation in natural mortality. Obviously, it's a lot more difficult to estimate that. There are some, at least, research papers looking into that. I was wondering, particularly Kai and Simon, if you have any sort of evidence of natural mortality and what the scale of that variability, mainly for adults too, or you know, maybe small ones, but not tiny ones where they've recruited to the fishery, where it's important for us to consider modeling it. Yeah, Kai, do you want to comment on that?
Well, I don't. It seems it's difficult enough for us to figure out what the constant average should be. And certainly for tunas, I don't. I think, you know, we get some of those out of you know, predation mortality models and so on, but I'm not aware of anything that relates to tunas that really would give us a strong lead.
What about for other species where there's a lot more data? Is there evidence of, particularly for adults, is there evidence of temporal variability and natural mortality, or is it fairly constant?
It's clearly less than for juveniles, but I couldn't actually make a well-supported judgment on that. So
yeah,
perhaps maybe Simon has an idea, or John.
Yeah, I know that at least in some cases they have sort of extreme events of mortality, like for red snapper in the Gulf of Mexico and things like that, where they have actual good indication of large mortality effects.
Right, we have some. So we have some red tide mortalities, for example, where that can be, but that's relatively rare. I mean, yes, it happens, and in those, but you know how that translates to places that have less sort of extreme events. And it would seem to me that in oceanic species, you would expect it to be relatively more constant, probably. But I'm just guessing.
Yep. Okay, thanks. Okay, any other comments on natural mortality? Yeah, Carolina.
I think I'll go for the what is the advice on a good practice in terms of what scenarios to include in in an ensemble model when you are addressing uncertainty in M. So what I'm hearing here, Kai was saying, okay, maybe don't use the older fish that you have, but the second, like oldest, there might be a sensitivity, perhaps, for example, the 18-year-old and then the 15-year-old or something like that. Another one that I was thinking is because growth and mortality might be correlated, then have a factorial design. You have high natural mortality and corresponding growth and vice versa. And the third one that I was thinking is the difference by sex ratios, mortality by sex, because at least in the EPO we don't know if we should go with growth or mortality. So those are the scenarios, but it starts to build up a lot of options there. So any thoughts of what at least the minimum should be?
Well, if I can start with one thought that I think absolutely that you should run some sensitivities. And actually it's something that bugs me that, say, in the region where I'm most involved in assessment panels in the southeastern US, the tendency has become to pick one value and stick with it. So we increasingly, 10 years ago or so, we would see a range of sensitivities to mortality assumptions, and somehow those have successively disappeared, and I think that's a bad thing. So I think you absolutely should have some sensitivities.
Yeah, and I agree with that. And the difficulty, of course, is that you can think of lots of different options, and those options do tend to blow out very quickly. That was really why I only proposed the two options of the two alternative maximum ages. But it's easy to think of other probably equally plausible ways of looking at uncertainty. There's a uncertainty distribution around those M estimates from the AMAX values of CV of 0.31, so you could use that to provide uncertainty distribution. And certainly the youngest females, the oldest females in most cases do seem to be slightly younger than the oldest males. So it is plausible that perhaps females do have higher natural mortality, or perhaps there's something else going on. In terms of, it's hard to recommend to any particular group what they should do, but those are the kinds of things to think about, I guess.
Thanks, Simon. Any other comments? Yeah, Kai-san. Sato-san.
In terms of the reporting rate of the tagging experiment for the longline fisheries, we recognize the importance of the close relationship between the scientist and the fishermen. So the more positive approach to the fisherman to interview or something like that. So we are welcome to your advice and suggestions to improve the reporting rate from the long-run vessels. Thank you.
Yeah, thanks. That would be great. Yeah. Okay, so we're nearly to the end of this. We've got another 10 minutes. But one thing I wanted to bring up was looking at multi-species models and estimating temporal variation and natural mortality for young individuals. Something that's big in non-tuna world. In the tuna world, has anyone actually been doing that? And particularly since we've got pretty high exploitation rate on juveniles, I'm not sure what the evidence is of per seine size or floating object size yellowfin, big eye, and skipjack being eaten by other predators that are in large quantities. But does anyone here have any experience with doing multi-species models for tuna or predation studies or anything like that? It doesn't look like it, so I guess that's an area we need to talk to our biologists in to get a better understanding if it's important or not. Yeah. Okay. Any other comments or questions on natural mortality? Or have we flogged it to death? Okay. So I guess we should finish the natural mortality section. The next presentation is going to be on weight, length, maturity, and conversion factors by Jed McDonald. So I guess we should probably go to that now if we can. So is Jed doing it online or was he here? No? Oh, so it's pre-recorded? Okay, good. We have 10 minutes to organize ourselves on that, so that's good.
Greetings everyone, Jed McDonald here from the Oceanic Fisheries Program at SPC in Umeå, coming at you from the Melbourne office. On behalf of my co-authors, it's a privilege. Greetings everyone, Jed McDonald here from the Oceanic Fisheries Program.
Give a pre-recorded presentation here by Jed talking about weight, length, conversion factors and maturity. So, okay.
Greetings everyone, Jed McDonald here from the Oceanic Fisheries Program at SPC in Umeå, coming at you from the Melbourne office. On behalf of my co-authors, it's a privilege to present this overview of SPC's recent work to improve weight and length data, conversion factors, and estimates of maturity for tropical tunas. Thanks very much to Mark and to Simon Hoyle for reaching out, and apologies that I can't be there with you all in Wellington to share the love and to chew the fat on this fascinating suite of topics. Given the natural connection between length and weight data and the conversion factors between these data types, I've rearranged the title of the talk to focus on these aspects first, before touching on some new approaches to estimating maturity later on. Length and weight data are key inputs into many stock assessments, including tuna assessments in the Western and Central Pacific Ocean. I won't harp on too much here about the size data available for WCPO tuna assessments, as Simon Hoyle and Tom Peatman, I trust, have already covered these topics in magnificent detail. But in basic terms, age-structured assessment models often need to convert length frequencies and numbers of fish per age class into biomass. A length-weight relationship, coupled with a growth curve, tells such a model how to convert numbers at age into spawning biomass. We want to get that conversion right, so good practice requires the collection of the highest quality data available on fish lengths and weights, and the development from these data of reliable conversion factors between length and weight. Enter Project 90. SPC has been provided with funding resources under WCPFC Project 90 to assist in length and weight data collection throughout the region and to analyse this data to help inform fishery management. Project 90 arose from discussions at SC13 that recommended SPC be tasked with 1. Designing and coordinating the collection of representative length measurements of bycatch and target species, and 2. Designing and coordinating the collection of length weight, and weight conversion factor data on all species. We provide an update each year to the Scientific Committee, and here's a link to the latest report from 2022. Project 90 supports and is linked to several current projects. 5 are shown here that I'll now detail further. One of the first Project 90 tasks was to update our conversion factor database, adding metadata on things like sample size, information on model fit, and details on the source and quality of length and weight data where available. We also expanded the database to include newly published conversion factor relationships across the range of target and bycatch species encountered in WCPO tuna fisheries. At the bottom, here's a link to the web tool we created to access the conversion factor database. This data is all publicly available, so Arnie will be proud, and it's updated regularly as new information comes to hand. A key motivation behind the web tool development is to provide a resource for conversion factor comparisons across oceans and to facilitate collaboration and meta-analyses. For those folk interested, I'd encourage you to check it out. In January 2021, SPC and colleagues at the National Sun Yat-sen University in Taiwan entered into an agreement regarding an exchange of big eye tuna length and weight measurements covering all SPC and Taiwanese data holdings. The primary objective of this work was to explore spatial and temporal variability in big eye tuna growth parameters across the WCPO, thereby addressing a key recommendation of the 2020 Big Eye assessment. These figures show the spatial coverage of paired big eye length and weight records from SPC and Taiwanese data sources compiled in this exchange. Shown are longline records from SPC port sampling, observer and biological sampling collections, and records from Taiwanese observers from 2008 onwards. Actual or inferred locations of capture are shown, color-coded by the length bin, and the total number of records exceeds 1.5 million, dating back to 1991. Eric Chang presented the initial results from this analysis to the POR in 2021. With reference to the plots on the right, Eric's results highlighted, first, how decisions around data preparation and filtering can have substantial impacts on the shape of the length-weight relationship, as well as the variability around mean weighted length. And second, the differences in the B parameter of the length-weight relationship derived from the Taiwanese data on the left panel, and that derived from the combined SPC and Taiwanese data on the right panel. Eric's analysis also revealed evidence of spatial and seasonal variation in the shape of the length-weight relationship across the WCPO and the EPO, particularly in the B parameters. Here, we've plotted the length-weight relationship fitted on data collected for each 2020 assessment region, plus a couple of extra regions, 10 and 11, that we've added in the EPO. The B parameters are shown in black next to the region number in brackets. Although sample size and data quality varied across the regions, we note that regions 10 and 11 in the east have significantly larger B values, shown here in red, compared with most other regions in the west. We also found evidence for seasonal, annual, and regional differences in big eye condition. We calculated the relative condition factor, KREL, which is given by the mean observed individual tuna weight divided by the predicted weighted length. This is a measure of tuna fatness and can be an informative indicator of ecosystem state, as we're finding in related work on ecosystem and climate indicators. The plot on the right shows the mean KREL by stock assessment region across all years. We see some patterns across regions, particularly lower condition in the EPO in regions 10 and 11 compared to the WCPO, but also high variability within regions. Simon Hoyle and Eric are currently extending this work by modelling how biology, environment, sampling location and time, and vessel and gear related effects can shape relationships between length and weight in condition across the region. The first results of this analysis will be presented to the POR in April. General Santos in the Philippines has provided a fruitful data collection collaboration for Project 90 work. This is one of the few locations across the region where large yellowfin and big eye are landed whole in port, and hence opportunities exist to fill knowledge gaps for key conversion factors. These include the UF to PS factor, which relates the fork length, UF, to the PS length, which is the length from the anterior base of the pectoral fin to the second dorsal. For yellowfin, we now have 6,581 records from the Philippines out of a total of 7,587 records from all sampling locations combined, with 826 of 1,360 records for big eye also coming from Gensan. The Philippines has also been our primary source of data on the critical gilden gutted weight, that is GG, to whole weight, WW relationship. This relationship, derived in Philippines fish alone, is applied to large longline caught tunas across the broader region, where the fish are predominantly gilden gutted at sea with no accurate measurements of whole weight possible. Data on this conversion factor are notoriously scarce, but through the last 2 years of collaborative effort with local industry partners in General Santos, we now have around 2,200 measurements for yellowfin and 198 for big eye. So still low numbers for big eye, but an improvement on data available for recent stock assessments. The Philippines ringnet fishery targeting juvenile yellowfin, big eye and skipjack also unloads in Gensan, providing unique opportunities for developing conversion factor relationships relevant for juvenile tunas. Otoliths and muscle tissue collected from these juveniles are also extremely valuable for studies of population connectivity and stock structure in these species. The figures on the right show the length weight relationships for yellowfin and big eye port sampled in Gensan between December 2019 and May 2020. The orange circles denote measurements from small, presumed young of year and age 1 fish. Blue circles are larger individuals. The curves, lines and equations on the plots represent best model fits to the data, plotted for small and large fish separately and for all fish combined. Touching back on the gilled and gutted to whole weight relationship, as the Philippines fishery catches relatively few large big eye and operates across only a small portion of the assessment regions for big eye and yellowfin, our recent efforts are focused on increasing the sample size for this conversion factor further afield. When fish are not unloaded whole in port, which is the status quo for longline unloadings across the region, one alternative is to remove the gills and guts at sea and then weigh them and the gilled and gutted fish they came from in port. This gives us all the weight measurements we need to obtain accurate gilled and gutted to whole weight conversion factors. Samoa has recently signed a letter of agreement with SPC to undertake this work on longline called big eye unloaded in Apia. If successful, this approach can then be rolled out more widely. This will boost the sample size for big eye substantially and is an important step in nailing down a reliable relationship for future assessments. The last of the Project 90 projects I want to present relates to testing the limits of electronic monitoring as a source of high-quality length data. By way of background, the use of EM technology to record fishing activities on tuna longline vessels operating in WCPO waters began in 2014. A key biological parameter which can be recorded by EM is the length of specimens caught and landed on deck, with lengths measured using a digital measuring tool. However, to date, length data generated from EM has not been used in stock assessments for WCPO tunas. This is partly due to a lack of agreed standards for measuring the accuracy and precision of length measurements made by EM as compared with fisheries observer and port sampled measurements. Yet with increasing amounts of EM length data becoming available and observer coverage on longline vessels remaining low across the region, making best use of this potentially rich data source seems like a good idea. To this end, SPC has recently teamed up with the Department of Resources Maritime in Tahiti, SatLink, the EM service provider, Nature Conservancy, and the fishing industry in French Polynesia on a study to compare length data derived from digital EM measurements and physical length measurements made by fisheries observers at sea and port samplers in port. Our first trial in albacore showed strong congruence between onboard observer and port sampler measurements. Focusing on the black circles, here we have length data for 77 albacore measured for fork length. Measurements made by fisheries observers at sea are shown on the y-axis, with measurements made by port samplers on the same fish after unloading in Papeete on the x-axis. We see fairly strong agreement between the observer and port sampled measurements. The red dotted line on the plot is the one-to-one line, and the black line is the mean prediction from a linear model with 95% confidence interval shaded grey. No significant difference was found between red and black lines. This is nothing earth-shattering and has been shown previously, but it does demonstrate the congruence between length measurements made at sea, often considered the gold standard of length measurements, and those made in port on the same fish. The orange circles represent EM length measurements made on a subset of 19 of these fish. In general, we see rather dramatic underestimation of length compared with the gold standard observer lengths. Taking the most extreme example, the fish measured by an observer as 105 centimetres fork length was measured as just 63 centimetres fork length by the EM digital measuring tool. The initial trial in albacore didn't inspire great confidence in obtaining accurate length measures from EM, but the sample size was small, and so we pressed on and examined paired measurements for more individuals from another longline trip. this time adding small numbers of yellowfin and big eye to the mix. For this trip, a total of 385 fish were measured across the 3 species. Here's the plot of the length measurements made by observers on the x-axis and those measurements made by the EM digital measuring tool on the y-axis, with the 1-to-1 line shown in grey this time. Again, length measurements for specimens made with EM appear consistently lower than length measurements made by the observer. For all 3 species, we see that bigger fish are underestimated at a much greater rate by EM than smaller fish. For albacore, where the length range is narrower than for big eye and yellowfin, the variation of EM measurements is much greater. Unlike the initial albacore analysis, it is encouraging to see some trends between the EM and observer measurements, and there is further potential for increasing accuracy in EM length measurements through improved calibration processes on the vessel. As new data rolls in, our analysis is expanding to test for any vessel, set, observer, and analyst level effects on the nature of these relationships. I'd like to chat now briefly about maturity, something clearly lacking in the current batch of SPC stock assessment scientists. Previous assessments for big eye and yellowfin in the WCPO have used maturity at age and more recently maturity at length ogives to define whether the fish are juveniles or adults. In the 2020 assessments, maturity ogives were the product of the fecundity at length, the proportion female at length, and the proportion mature at length. The spawning fraction was not included as the data available from the EPO were considered unrepresentative. Estimation of several of these reproductive parameters has typically relied on histological examination of gonads sourced from biological sample repositories such as the Pacific Marine Specimen Bank. This work is challenging, time-consuming, and takes specialist skills, and hence is not updated frequently enough, although some new analyses are available. However, new innovative techniques to reconstruct an individual fish's maturity and spawning history using otoliths have recently emerged. These otolith-based techniques remove the need to directly assess fish gonads. Instead, they focus on estimating an individual's size and age at maturity and spawning frequency by mapping newly discovered reproductive proteins and hormones that are trapped within the growing otolith matrix, and then using proteomics and biochemical 3D visualization tools to do the mapping. Further development of these novel techniques and concurrent work testing the sensitivity of chemical markers like zinc within otoliths to the onset of maturity and spawning will, in due course, create opportunities to streamline how maturity data is collected, allowing us to produce lifetime diaries of maturity and spawning for individual fish. We're currently trialling the first application of the method on albacore through a FRDC project in collaboration with the University of Melbourne, with the first results due towards the end of this year. Stay tuned. So, to sum up the talk in the context of tuna stock assessment good practices for weight, length, conversion factors, and maturity, first, I think a continued focus is needed on collecting and using the highest quality length and weight data available in assessments. Best practice would require this data to be a perfect representation of the fish population, free of all bias. But is this ever really possible? Good practice means that assessment scientists make concerted efforts to understand where the data comes from, allowing informed decisions to be made on its quality and its limitations before it goes into the model. To obtain the best quality data, collaboration among RFMOs, research institutes, and the fishing industry is key, something that becomes simpler if data, or at least informative summaries of it, are made publicly available. A good practice, and one that I hope might spark some discussion in the group, following on from the outcomes of the recent Wellington peer review, would be to find ways to investigate the impacts of incorporating the variation observed around the mean conversion factor relationships on model outputs. As an example, the plot on the right shows the length-weight relationship used for the 2020 big eye assessment. The red and green circles represent measurements from 2 databases representing different years of sampling and the black line represents the mean weighted length for all the data combined. We see a huge amount of variability around this curve that is not captured in the mean relationship. Clearly, good practice would be to capture this variability in the assessment model, but how might best this be achieved? Fourthly, building and refining models for conversion factor parameters reflective of fish growth and condition might lead to better predictions on how these traits link to a species' biology, surrounding environment, where and when it was captured, and how fishing may be impacting. Finally, we recommend pursuing research into new approaches for estimating maturity for tropical tunas, for example through odorless and other statistical methods. But we also emphasise the importance of continuing with and borrowing strength from traditional approaches where possible. Thanks very much.
Jed is not online today, and we're going to have the discussion tomorrow. So we'll wait for tomorrow to ask any questions. We have a bit more than 10 minutes left. So Nicholas is going to give us a presentation on process variation and sample size estimation, which is a topic we forgot to include in the program. So I think this will help us with some of the discussions we'll have in the next couple of days in terms of things like selectivity, about the weight length frequency data that we talked about earlier on. Able to must be it one, I hope. Copy and paste it over.
Yeah, hi everyone. Mark asked me yesterday if I might put together a couple slides on some recent research. And so I apologize in advance. My presentation is quite crude. It was literally put together in a day. But the research concerns a couple of studies aimed at looking at how we should weight our composition data within stock assessment. So whether we should be estimating the sampling variance internal to the assessment using an iterative method or setting it outside the assessment. And also the interaction between estimating the process variance, so maybe allowing for time variation in processes within the assessment and the interaction of estimating both of them. And so the first study we looked at was in a simulation estimation framework, simulating a variety of different levels of overdispersion in your data and a variety of different levels of model misspecification, particularly with respect to selectivity. We fit a suite of assessments to the data under a number of different ways to weight the composition data using iteratively weighting, using a variety of different likelihoods that might be able to be weighted within the assessment, and found that over most of the scenarios, the Dirichlet multinomial actually performed quite a bit better than most of the other methods. And frankly, it performed about as well as, and in many cases better than the Francis iterative reweighting method of the multinomial. And so we suggested that, and what it was doing was, it was able to do that because it was accounting for both overdispersion as a function of the way in which the data were sampled, at least some of it, and further downweighting for model misspecification, in this case in selectivity. And so, yeah, we first lesson would be, we recommended from that paper to estimate the sampling variance of composition data internal to your assessment using the Dirichlet multinomial, because that allows you not only to account for that overdispersion in the data, but also possibly account for some model misspecification as well. So then we followed this up by thinking, well, what if instead of allowing that sampling variance likelihood to account for that misspecification, what if we explicitly modeled that process variation or some of that process variation within the assessment, along with the sampling variation. And so we looked at a couple of different scenarios in terms of process variation in a simulation operating model. And that top row is whether selectivity is constant or time varying. Then our bottom row is whether catchability is constant or time varying. And in assessment models, we modeled those with Haikung's 2D AR1 method, which estimates age and year specific deviations in selectivity and should be able to theoretically allow for a time varying pattern. And for catchability, a random walk pattern. And so I won't talk about catchability anymore today. What I'll just say is that for the scenarios where there was catchability in the operating model, and you estimate it in the estimation model, estimated a degree of variation and led to considerably less bias than the models which did not estimate that variation. And when there was no variation in the operating model, but you allowed it to vary in the estimation model, what was occurring was the variation would essentially tend to zero and result in a model that was identical to the model that did not allow for that variation. So there was no real downside to specifying it. Now, with respect to fishery selectivity, we sort of, and as I alluded to with the catchability debate, looked at three separate questions. Can you estimate the variances simultaneously when the model is correctly specified? So when you do have that variation in selectivity, you're estimating that sampling variance internal to your assessment. Can you also estimate the parameters of that 2D AR1 method, along with recruitment variation? And then what if the process is not varying in the operating model or in the real world system, and you allow it to vary within your assessment model? Is there a downside to that? And then what if you allow for that variation in a process in your assessment model, and a completely different process is actually the one varying in the operating model? What are the downsides to that? And so the first situation, when you're sort of correctly specified, that is when you have variation in your operating model and selectivity, and you allow for it in your estimation model, what we found is that, well, I'll just go through this figure first, is the green dots are the estimation models without process variation in selectivity, and the triangles are those that allow for process variation in selectivity. We're looking at median relative error of depletion in the assessment here. And as you go from left to right in each one of these panels, the sample size and the information content and the composition data increases. And so we found that it was estimable when you were correctly specified, and it resulted in a great reduction in bias compared to not specifying that variation in selectivity at all. And as you can see here, the degree of improvement in bias was certainly conditional on the sample size of the composition data and the information content in that composition data. Although even at the small sample sizes, in some cases, it still did improve upon the model with no process variation, and certainly didn't result in decreased performance. Okay, now the situation where the process is not varying in the operating model in the real world, and you're estimating it or allowing it to vary in the assessment model. What we found was what those process variances were doing, similar to catchability, was tending to zero, resulting in an identical model to had you not specified that variance in the process to begin with. And so there was no real downside to specifying variance in these cases. So now what if we place those 2D AR1 deviations on natural mortality, when what's really varying in the operating model is fishery selectivity? And this sort of came up in the discussion the other day. And as you might imagine, what was occurring was the deviations in natural mortality were accounting for what was actually deviations in selectivity, and resulting in much more bias than not modeling variation in any of those quantities at all. And so there was a significant downside to misspecifying that variation in that sense. And this also came up in the discussion. What if you put that process variation on multiple quantities to try and get at least one of them right, and at least some of that variance? And so we had some mixed results with respect to this, in terms of we put those variation on M and on selectivity. When it was a simpler process variance formulation on M, like a random walk on M, then we could get the variance to tend to zero, and it would be identical to a model that only estimated variability in selectivity. But when they both had that two-dimensional AR1 structure, it was still highly confounded and estimated quite a bit of variability in M, and resulted in a lot more bias than had you not specified variation at all. So you can't get away by specifying it on a bunch of different processes. So some lessons learned from this. I certainly would argue that you should first try and estimate the composition data weighting internal to your model using the Dirichlet multinomial, I think, as a first go. I think this removes a lot of the subjectivity we've seen in how we're setting effective sample size across the different RFMOs for the Persane and long line data you saw on the first day. It's able to account for that over-dispersion data and can mitigate some degree of misspecification, particularly for processes closely linked to that composition data. As far as process variance goes, I would certainly argue that you should, as Andre mentioned, estimate that recruitment variance internally. And in all these scenarios, we did so. The rest becomes an interesting debate, given the perils of getting that variance wrong and how much worse the model performs in not specifying the variance at all. Some notes with respect to tunas. The last section was quite clearly done in a mix effects framework, which, as Andre noted, you need to do to be able to estimate those process variances as opposed to pre-specifying them outside of your model. Or you could go with a Bayesian approach. Now, I'm not aware of any tuna assessments that are fit in a mixed effects framework. I don't know that synthesis or multi-fin allows it, but there is the Woods Hole assessment model developed at NOAA that seems to be catching on among a lot of practitioners and might be an avenue forward in tuna fisheries. These simulations were based on having age composition data, which as we've talked about at length in the last couple of days, we often only have size composition data in tuna fisheries, and we're seeing those through the added lens of growth, which really muddies up that information content with respect to age-structured models. And then, as always, it was based on a conveniently simple simulation experimental framework, where tuna models are notoriously noisy with, it may become harder when you add in 10 to 14 fleets and estimating 10 to 14 over dispersion parameters. Although I don't know that that's reason to not attempt it. We also simulated a survey for half of the time series in each of these studies, which is notoriously unavailable in most tuna fisheries, which probably helped ground a lot of those process variances. So I had a slide thinking about the best way forward as to modeling process variance in tuna assessments and assessments in general, but given we're not even fitting models in a mixed effects framework yet, the debate seems a little academic at this point. And so I'll leave you with these three suggestions. I'll reiterate, I think that you should estimate the sampling variance, or at least attempt to estimate the sampling variance for those composition data sets internal to your model. I think we should be moving to mixed effects models, which is also what Andre noted in his talk. And then, as a starter, the low-hanging fruit, estimate that recruitment process variance, or begin to estimate it internally. And then we can have the debate over, which aspects of your model might be time varying. Although it was interesting, I think we just concluded in the M section, or at least Kai did, that there's not much evidence for time varying M in many different systems. But debate for another time. One thing I want to note is I didn't know about the negative bias in recruitment variation that Andre brought up when you're modeling size composition, which is an interesting nuance. But that's all I had. So thank you.
Thanks, Nicholas. It's getting to the end of the day, but if we have a quick question or two, Rich.
Sort of two questions. The first one was on smoothness. AR1s, they're sort of differentiable nowhere. You can wind up specifying that process for time variant selectivity, and especially in a Bayesian sense, when you actually look at the draws from the posterior, they can be very herky-jerky, especially with age, and you just think, that's strange, but that's just a misspecification. That if you generalize to a sort of more flexible Gaussian process, like a Mattern or whatever, you can start to specify that you're going to want to see some level of smoothness in those profiles. It doesn't invalidate any of the approach, just the specification of the Gaussian process is important. And the second one is projections. Because when you've got an unbounded process, eventually everything's going to blow out everywhere if you try to project forward into the future. And again, thinking about beforehand how you'd specify the Gaussian process, when you have to think about, if you have to do projections, just a random walk is eventually just going to go everywhere. And that's going to just blow everything out. Do we need some sort of, if you're going to specify that kind of process, do you want it to be bounded? Or do you want it to be like a pure random walk? Just a couple questions or comments.
Yeah, do you have a response? Or?
No, other than, I don't know if I captured the entirety of that second component, but I think many have used moving averages to project at least at the very small scale.
Okay, well, I think we should end it for the day. And I guess in the discussion sessions that go in the next couple of days, if you have a question on this, it can come up and Nicholas can answer it, or see him in the breaks and things like that. Otherwise, let's finish, and tomorrow we're coming back and starting with growth at, we're going to discussion on the weight length stuff at 8:30 in the morning, and you can ask Jed some questions on his presentation. And I think we have a dinner or something tonight.
The dinner is at Mac's Brew Bar in Taranaki Street down on the waterfront at 7 o'clock.
Is that like the traditional Mac's from a long time ago, or is this a different one? Like Mac's, Black Mac and all that? No?
I don't know.
I think so.
It is.
I saw it there on Google Maps, so I know it's there.